In continuation to the last class, we have seen that if the particle is experiencing a magnetic field which is directed along z axis, the particle's velocity is written as Vx, Vy, Vz, starting from the Lorentz force expression, which is q times V cross B. We have realized that the work done is 0 and energy is constant. So, when you break this cross product and if you couple the equations in terms of Vx and Vy, we have realized three equations which are d square Vx by dt square is equals to minus omega square Vx d square Vy by dt square as minus omega square Vy and d square Vz by dt square as 0. Now, we have also seen that these second order differential equations can take a simple harmonic solution such as Vx as a cos omega t and plus b sin omega t. We have realized that Vx, if you take a double derivative of Vx and if you substitute this into these equations, we will get the same. We will realize that this equation will satisfy the second order differential equation. Now, we have to find out the values of these two constants a and b. And right now, we do not want to assume what will be the form of Vy, let us say, instead of Vx. We should also have the form Vy. Now, the objective is we want to see how will Vx and Vy look like in the absence of these two constants. What can they describe? What can they describe about the particle's trajectory? How will the particle's velocity will look like? Now, at this point itself, we can say that from the second order differential equation, Vz will remain a constant, because the particle is traveling parallel to the magnetic field, so it will not be influenced by the magnetic field. Okay. Now, if you want to calculate the values of these two constants, we need to use some conditions, some, let us say, the boundary conditions. So, at time t is equals to 0, we can say that velocity Vx will be V0x. If you use this condition in this expression, let us say number 1, we say that V0x is equals to a into 1 plus b into 0. That means the value of a is equals to V0x. So, now itself we can write Vx is equals to V0x cos omega t plus b sin omega t. So, now we need to find out the value of the constant b. Okay. Now, from the original expressions a, b, c, we can write that m dvx by dt is equals to q vy b. This expression means that the solution Vx and Vy are related. They are related. So, if you write a solution for Vx, you should very well be able to write Vy if you know this expression. Now, what we can do is we can use this expression in combination with this expression to get the value of Vy. Okay. How do we do that? Now, we can differentiate Vx. So, we can write q Vy b is equals to minus m times a omega sin omega t minus b omega cos omega t, or we can write qb by m times Vy. So, we have started from Vx, by the way, is equals to minus omega A sin omega t minus B cos omega t, right. So, in that case we can write V y QB by m is omega is equals to minus omega A sin omega t minus B cos omega t. So, we write V y is equals to minus A sin omega t minus B cos omega t. So, having known the values of constants already, we can write V y is equals to A is already V 0 x sin omega t plus B cos omega t. At this point, we can write the condition as at t is equals to 0, V y should be V 0 y. Using this condition into this expression, we can write V 0 y is equals to V 0 x into 0 plus B into 1. That implies B is equals to V 0 y. So, we also got the value of the second constant. So, A, the constant A is V 0 x and the constant B is V 0 y. Now, with this the values of these two constants, we can write V x is equals to V 0 x cos omega t plus V 0 y sin omega t, and V y is equals to minus V 0 x sin omega t plus V 0 y cos omega t, and V z is equals to V 0 z. That means V z, or the velocity component along the z direction or along the magnetic field's direction, is uninfluenced. Okay. And the second most important thing is the velocity along x direction has an initial component of velocity along the y direction, and the velocity at any given time along the y direction has an initial component of velocity along the x direction. So, Vx has V 0 x and V 0 y, Vy at any given point of time has again V 0 x and V 0 y, and velocity Vz is just a constant along z axis. Now, what we have to understand, what are these equations telling us? So, to understand, let us say, what do we have? We initially had Vx, Vy and Vz. Then in combination with this, we had the initial velocities as V 0 x, V 0 y and V 0 z, right. Now, what are these? These are the velocity components, of particle in the presence of external field. So, we know these three components are out of this cross product V cross B. That is very important. How is the magnetic field coming into picture? It is coming into picture by the omega, which is QB by m. Now, let us try to understand how these three velocity components can be combined for a physical interpretation of the result. Okay. Let us square and add Vx, Vy and Vz. Vx square can be written as V 0 x square. So, this is cos square omega t plus V 0 y square sin square omega t plus 2 V 0 x V 0 y sin omega t cos omega t. Similarly, Vy square is written as V 0 x square sine square omega t plus V 0 y square cos square omega t minus 2 V 0 x V 0 y sine omega t cos omega t. If you add these two, let us call the expression for Vx as equation A, expression for Vy as equation B, expression for Vz as equation C. If you square and add, if you add these expressions, adding these two, we will realize Vx square plus Vy square is equals to V 0 x square plus V 0 y square, which we are going to call as V perpendicular square, because Vx and Vy are perpendicular to Pz. Okay. Now, from here itself, what can you say about the trajectory of the velocity of the particle? It is circular. It is executing. The particle is executing circular motion, because this expression looks like an equation of circle, right? So, Vx and Vy are combining to give circular motion along or in the xy plane, circular motion in the xy plane. What happened to the z axis? What is Vz doing now? Vz is so what is Vz doing now? Vz is a constant which has remained at the same value over the period of time. So, with time Vz is a constant, right. Now, what is Vx and Vy doing? Vx and Vy are executing circular motion in the xy plane and Vz is a constant. Now, let us consider how will the particle move. So, the particle's trajectory can be more easily established if you find out the values of position with respect to time starting from the velocities. Okay. Let us say we write Vx as V 0 x cos omega t plus V 0 y sin omega t. So, which is dx by dt, right. So, if you integrate this expression to get x is equals to V 0 x sin omega t divided by omega minus V 0 y cos omega t divided by omega. Let us call this expression as d. Okay. Similarly, we can integrate integrating Vy, we will get y is equals to V 0 x cos omega t by omega plus V 0 y sin omega t by omega, right. Let us call this expression as equation number E. Now, squaring and adding equation D and equation E, what we will get is x square plus y square is equals to V 0 x square by omega square plus V 0 y square by omega square, which you are going to call as V perpendicular square divided by omega square. Now, what do we have? We have x square plus y square as V perpendicular square divided by omega square. Now, what is xy? Xy denote x, y denote the position of particle, right. they are suggesting that the position of the particle is varying with respect to time as if it is executing a circular motion. So, this equation represents a circular motion. Okay. Now, so the particle has experienced the magnetic field. The magnetic field was in this direction, right, Bz. Now, the particle is experiencing circular motion like this. What is the circle? Circle is in the xy plane. Okay. So, the velocity Vz, what is velocity Vz doing? Vz is constant. That means the particle is having a non-zero component of velocity along this direction. At the same time, the x and y components of the velocity are executing circular motion. So, this gives you the what we call as the helical motion of the particle. So, particle is executing circular motion, and because of the non-zero component of the velocity along the z direction, the particle is pushed in the positive z axis. Okay. So, this kind of movement is generally called as the helical path or helical motion. Now, we need to find if this is the circular motion. I mean, on the right hand side, this is of course the radius of the circle, and this is the plane in which the circular motion is executed. Now, let us find the radius of the circle, of this circular motion. Okay. Now, we can write the radius RL as V perpendicular by omega. So, V perpendicular is the velocity in the perpendicular direction, omega is the frequency, QB by M. Omega, what is omega? Omega is the frequency, angular frequency, in terms of which is QB by M. If we recollect the relations, so omega is the angular frequency which is written as QB by M. So, we can write the frequency as QB by 2 pi M, and the time period of this execution is 2 pi by omega, which is 2 pi M by QB. Okay. Now the radius of this circular motion is written as M, or radius as V perpendicular by QB by M, which is M V perpendicular divided by QB. So, this is the radius of circular motion. This is called as the radius of gyration. The particle is gyrating in this direction, in this way, and this is called as the radius. This is the radius of gyration. Okay. Now, what is specific about this radius of gyration? Radius of gyration is proportional to the mass of the particle and is inversely proportional to the charge and to the amount of magnetic field that you apply. And radius of gyration is proportional to the velocity, the perpendicular velocity of the particle. That means, the more the mass, let us say, so that means that the ions will have larger gyration radii and the electrons will have a smaller radius of gyration. So, electron circle will look like this and the ions radius of gyration will look like this. Now, where are we? So, now we have, so in terms of this, so we can write x square plus y square is equals to m v perpendicular by qb square. So, this is the circular motion and this is the radius. Now, from this the circular motion is executed at the center. So, the particle is entering into the magnetic field at the origin. Okay, so that is the idea. Otherwise, the circular motion is executed around a center which is x0, y0. This point around which the circular motion is executed is generally called as the guiding center. Guiding center is the imaginary point around which the circular motion is executed by the particle. So, the particle is executing a circular motion like this. So, the imaginary point around which circular motion is executed is called as the guiding center, like this. Okay. Now, if you observe carefully, the x component of velocity and the y component of velocity combinedly are giving you the circular motion, and the z component of velocity is pushing the particle linearly along the z direction. Okay. So, this movement that you see the particle to be going in this way is due to the z component of velocity, and this movement in this xy plane. So, this is the z direction. So, this movement in this xy plane, this movement is due to Vx and Vy. So, this is the role. So, magnetic field is influencing only along Vx and Vy. That's the reason that we called Vx and Vy as V perpendicular components and Vz as V parallel component. So, as a conclusion, what you can say is that the perpendicular component will impart circular motion and the parallel component will impart linear motion along the z axis, along the direction of magnetic field, circular motion in the xy plane. Okay. Now, so what we can say is that, so Vx and Vy are generally referred to as V perpendicular, as they are perpendicular to the applied magnetic field. They are the components of velocity which are influenced by the magnetic field, and they are executing the circular motion with a radius of RL, which is called as the radius of gyration. The third component Vz can be referred to as V parallel because it is parallel to the external field that is applied. The guiding center around which the circular motion is executed is generally taken as x0, y0. Okay. The parallel component of the particle's velocity allows it to move linearly with a velocity v0z, a constant velocity along the z direction or the direction of the magnetic field. Okay. So, at the same time, the perpendicular component gets influenced and they move circularly around the guiding center. So, we can say that the particle moves in a helical path. So, this movement that you see is a helical path in which the particle is progressing along the z direction by revolving around or revolving in the xy plane. Okay. Now, we can write. So, what you see here is that, what you see carefully, if you take the guiding center, if the particle is moving in this way, the guiding center is moving in the, so this is the guiding center around which the particle is moving. This is the guiding center and this is the guiding center around which the particle is moving. We can write that the position of the guiding center, let us say, the position of the guiding center with respect to time, because there is a linear velocity that is involved, right. So, x0 in the x direction, y0 in the z direction plus z0 plus v parallel times t along the z direction. Now, you see x0, y0 is the center of this radius. So, this is in the, so they are constant, right, and z0 is the initial point at which the velocity starts to get influenced by the magnetic field. So, this is the parallel component of velocity which is parallel times t. So, with time this Rg gives you the position of the guiding center with time. Okay. Now, generally what you, if the particle enters the field at the origin, we can say that x0, y0, z0 are to be treated as 0, 0 and 0. In that case, the expression for Rg simply becomes V parallel t along k cap. Okay. So, hence we can say that the guiding center is moving along the z direction. Okay. Now, the most importantly, now comes the circular motion of the particle and the particle's polarity. Now, here we have seen that the mass of the particle is coming into picture by to influence the RL, right. So, RL was defined as mv perpendicular by qb. So, omega is qb by m, right, and RL is m v perpendicular by qb. So, these two are very important relations. Important in the sense that the mass of the particle is able to influence the frequency of this rotation and as well as the radius of this particular circular motion, right. So, here in addition to the mass, where does the charge come into picture? Charge comes into picture in both the places. More importantly, charge. So, if you have a positive charge and if you have an electron or if you have an ion, the direction in which the circular motion is executed will be different. So, generally let us say what happens is, by applying the right hand rule, you can realize for yourself that an ion will always drift or will always revolve to its left. So, this is an ion, that means it will go like this. And an electron, let us say if the origin is shifted here, electron will revolve to its right. Okay, now electron will revolve to its right. Now, what I have done is I have kept the radius of gyration of electron small so that the effect of mass is reflected in the picture. So, this is an electron and this is an ion. Okay, that means more the mass RL will be larger. So, this is the idea. Now, what have we understood? We have understood that if the particle is experiencing a homogeneous static magnetic field, then number 1, the energy is conserved, Number 2, no work is done, work is 0, no work is done by the field. Number 3, the particle's trajectory will be circular in perpendicular direction and linear in parallel direction. Okay. So, this is discussion about single particle motion in terms of in the presence of a magnetic field. Okay. Now, we will in the next lecture we will try to see how the particle's motion will be in the presence of an electric and a magnetic field. Now, we have seen how will the particle move only in the presence of an electric field, then we have seen how will the particle move in the presence of only a magnetic field. Now, we will combine these two pictures and see how the particle's motion will be influenced by both the electric and magnetic fields. Okay. Thank you.